Types of aqueous solutions and solubility. So let's think about two solutions that we are familiar with, salt water and sugar water. So salt water is sodium chloride, table salt dissolved in water. Sugar water is a solution, a homogeneous mixture of sugar, sucrose, in water. You can try this at home. You have 2 glasses of water, put a teaspoon of sugar into one, put a teaspoon of salt into the other, stir them up. They both appear to disappear. They seem to disappear. And it looks like exactly the same thing is happening. It's a similar process, but it's not exactly the same. How do they do this? How does salt disappear into water? How does sugar disappear into water? Sand doesn't do that. Dirt doesn't do that. So what happens? Well, we've got interactions between the particles. So in sodium chloride, we have ionic bonds, forces of attraction between positive and negative ions that keep table salt as a solid. In sugar's a solid at room temperature. Something is holding the molecules together. We'll talk a lot more about what that is later, but now we're just going to call it interactions. So there's a force of attraction between the sugar molecules. The water in the cup is a liquid, not a gas floating around because of attractions between the water molecules. So we have all this attraction going on here. When you mix a solute and a solvent, now you have some new interactions that can happen. Here are the solute-solute interactions. You also have solvent-solvent interactions. But when you mix them together, now you can also have attraction between the solvent molecules and the solute molecules. And whether this substance will dissolve in water or not has to do with the relative strengths of the forces of attraction. If the forces of attraction between the solute particles are really strong and there's very little attraction between the solute and the solvent, it's not going to dissolve. This is going to be like a clique of mean girls at school. They're just so stuck on each other. They just go around as a little pack, right? And they're just not going to have any positive interactions with anybody else. Some of you are smiling. You knew some of those people. If there is attraction between the solvent and the solute, then the solute molecules are willing to move apart and mix and mingle with the solvent. Okay? Let's look at a water molecule. Here's a space-filling water model of water molecule. If we look at the distribution of electrons, what we find is that they're not evenly distributed. The water is an electron, the oxygen is an electron hog. Water is a covalent molecule, and so there's a covalent bond between the hydrogen atom and the oxygen atom that involves sharing of electrons. But you can share without sharing equally. This is what happens when a big brother and a little brother share a cookie, right? The big brother gives the little brother the little piece, and he's too little to know the difference. So yes, I shared my cookie with my baby brother. Yeah, you gave him like 3 crumbs. It's sharing. These guys don't share equally. Oxygen hogs more of the cookie, okay? He takes more of the electrons. And he's also sharing electrons with this other hydrogen. He's doing the same thing over here. So at least he's being fair about it. This end of the water molecule is going to have a partial negative charge because of that. Because there's more electron density over here than at this end where the hydrogens are. This is not an ion. It's not an ionic compound. It's a partial charge. In an ion, you'd have a +1 and a -1, or bigger. Here, maybe you have a 0.15 negative and a 0.075 positive. It's a partial charge. So when we put sodium chloride into water, sodium chloride has sodium ions and chloride ions. The sodium ion is attracted to the negative end of the water molecule. There's an attraction there. The chloride ion is attracted to the positive end of the water molecule. And so because we have interactions, significant interactions between the water molecules, the solvent molecules and the solute, the sodium chloride will dissolve. These ions will separate from each other because this attraction that they're losing between the oppositely charged ions gets made up for by the interactions with water. It's not just one water molecule that's going to come around the sodium, it's going to be a whole bunch of them. Like this. So here's our sodium ion, and the negative ends of water molecules are going to be attracted to it and kind of cluster up around it, sort of like circling the wagons. It feels, this ion feels comfortable moving away from its original lattice here because those interactions that it lost have been replaced by interactions with water. And over here, chloride gets surrounded by the positive end of water molecules. And so I think of these water molecules as luring these ions away from the mothership, right? Oh, come on out and play. We'll surround you. We'll make you feel comfortable. We'll be friendly to you. And so then they get lured away and they get all mixed up. So what you have at the end is ion particles now that are free to move around the solution. And they can move around and they will form a homogeneous solution. They will be completely, thoroughly mixed. Because we have these particles with charges that can move, this solution can conduct electricity. Electricity is the flow of electrons. In order for a liquid to conduct electricity, there has to be some means of transporting electrons. And these ions are the transport for the electrons. So this is considered an electrolyte solution. Where do you hear about electrolytes outside of chemistry class? Gatorade, right? You got to replenish your electrolytes. They're actually using the word in very much the same way. Electrolytes are salts, ionic compounds, not just table salt. You also need magnesium and potassium and some other things. When you sweat a lot, like I feel like I'm doing right now, when you sweat a lot, you lose the salts. That's what makes white stains on your shirt, you know, when you've been out golfing when it's 106 like my husband used to do. And he'd come home and his shirt would be all like crusty with salt because he sweated so much. You lose electrolytes. Your body needs those electrolytes to function. So when you sweat a great deal, you do need to replace that. Now, most people going for a little jog or a bike ride do not need to be drinking Gatorade. Water is actually better for most things, but that's what electrolytes are. Electrolytes, when dissolved in water, form a solution that conducts electricity. So they are soluble ionic compounds. Not everything that dissolves in water will conduct electricity. Non-electrolytes dissolve in water, but they don't conduct electricity. These include most molecular compounds. So sugar is a molecular compound. If you put sugar in water, it will not conduct electricity. So here we have a salt solution. This is a conductivity apparatus. It's a light bulb connected to a battery. And instead of this wire being connected, we have two electrodes that are in the liquid. In order for the battery to conduct electricity through this circuit and light the light bulb, there has to be a way for electrons to travel between these two separated electrodes. Sodium chloride dissolved in water allows that to happen. If you put sugar in the water, it does not form ions, and so there's no way for the electricity to get from one electrode to another, and the light bulb doesn't light up. When sugar dissolves in water, here's our sugar molecule. You can see there are oxygens and hydrogens on the sugar molecule, and they're sharing electrons unevenly, just like the water is. And so here's a hydrogen that is having its electrons sucked away from it by an oxygen. So it has a partial positive charge. It's going to be attracted to the partial negative charge on a water molecule. And so sugar will dissolve because it has these partial charges on it as well that can interact with the solvent. But it doesn't form ions. And so it will not conduct electricity because there are no ions to carry the charge. We talked about acids and learned how to name them. Remember, acids are molecular compounds that ionize when they're dissolved in water. They form hydrogen cations and anions. The molecules get pulled apart by their attraction for the water. So they're not ions in their pure form, but when you put them in water, the attraction they have for the water molecules is so strong that it actually pulls the molecule apart into two ions. So here we have acetic acid, and this acidic hydrogen on the acetic acid, that's a tongue twister, gets pulled off, leaving the acetate ion, and then here's the hydrogen ion. Strong acids will ionize completely. So in the video, he put a little bit of HCl in the water and the light bulb lit up very well. That's because when you put HCl into water, it separates completely into hydrogen and chloride ions. There are no molecules left. But with a weak acid, only a small percentage of them ionize. So things like HF, hydrofluoric acid, and acetic acid are weak acids. And so when we show them dissolving and forming ions, we use a double-headed arrow, meaning we understand that it does not go completely to the products. It's kind of in between, and actually it's a lot less than 50%. There's more of the molecule present than hydrogen ions and fluoride ions. But it does form ions, that makes it an acid. It will conduct electricity, but not as well as a strong acid. So strong acids ionize completely, they are strong electrolytes. Weak acids ionize partially, they are weak electrolytes. Yeah, I just said all that. So here we can look at pictures. Here's sugar water, and in the conductivity tester, we see no light at all. That's because when we look at the particles in the solution, there are no ions. No ions means no electric current. Here's the acetic acid. This is a weak acid, and so a lot of these acetic acid molecules are intact, but there are some ions present. And so the light bulb glows weakly because it's a weak electrolyte. There are a few ions, but not a lot. And here, sodium chloride is a strong electrolyte. All of those ions separate from each other, and so we have a lot of ions, and it can move electrons very nicely. You could think of it as like ferrying people across a river, perhaps. Each of these boats, each of these ions is a boat that could carry an electron. And so if you've got a lot of boats, you can carry a lot of electrons. Here, if you've only got one or two boats, it's going to take longer. You can't get electrons across the river as fast. I don't know where that came from. Any questions? So when an acid dissolves in water, it ionizes. It wasn't ions before, it's becoming ions. When ionic compounds dissolve in water, they were already ions, so we don't say they ionize, but we say they dissociate. They separate. So ionic compounds dissolve, and it's called dissociation. So the ions separate from each other. If you have ionic compounds with polyatomic ions, so like sodium sulfate, sulfate is a polyatomic ion. When this compound dissociates, these two sodium atoms, sodium ions, get separated from the sulfate, but the polyatomic ion stays together as a unit. And that's why it has a name as a unit, because it doesn't separate into sulfur and oxygen ions. It stays as sulfate. So we've talked about ionic compounds dissolving in water, and then you've got separated ions. Many ionic compounds dissolve in water, but not all of them do. So we have the terms soluble and insoluble. Soluble means it will dissolve in water. Insoluble does not dissolve in water. But this is Chem 1A, and so I need to tell you that even an insoluble compound dissolves to some extent. So we're looking at sort of a generalization here. If you take a teaspoon of sodium chloride and you put it in a cup of water and you stir it, it's very obvious that it dissolved, right? It disappeared. If you take something like silver chloride and put a teaspoon of that in the water and stir it and stir it and stir it, what you're going to see is silver chloride sitting on the bottom of the beaker. We say that's insoluble. That does not mean that no silver ions are present in the liquid. It does not mean that no chloride ions are present in the liquid. It means that so few are present that it's not worth messing with. It doesn't matter. A few of them dissolved, but it doesn't matter. Most of them don't. So that's what insoluble means. Silver nitrate forms a strong electrolyte solution, dissolves very nicely. Silver chloride, not so much. So this is what you would see if you put silver chloride in solution. Okay, most of it just sitting on the bottom. Well, how do we know if something's going to dissolve or not? There's a lot of factors in this, and so it's not easy to predict. It's actually quite complicated. The best we can do is to make a set of rules based on empirical observations. So people did tests, like, they sat around with beakers of water and different ionic compounds, and they stuck some in there and stirred it up. Did that dissolve? Yes. Okay. Did this dissolve? No, that one didn't. And lots of different people tested this and compared their results. And then they looked at the results, and then you try to see patterns in it so that you don't have to memorize everything. So this empirical method, we get some rules that can help us to predict solubility. So here are the solubility rules for ionic compounds as presented in your textbook, and these are the ones that I want you to learn. Okay, you need to remember these. And it may seem a little daunting. It's really not that bad. So the first part of this is a list of things that are usually soluble. So if it has lithium ion, sodium, potassium, or ammonium in it, it's going to be soluble. And then over here, some of these have exceptions. There's no exceptions. Lithium, sodium, and potassium are in the group 1. So those group 1 metals, if you see that as the cation, it's going to be soluble. It doesn't matter what the cation is. If you see ammonium as the, doesn't matter what the anion is. If you see NH4 plus as the cation, it's going to be soluble. Nitrate and acetate compounds are all soluble. So those are nice, there's no exceptions. Then we have the halides, chlorine, bromine, iodine. These are soluble except with silver, mercury 1, and lead 2. And then sulfate compounds are usually soluble except, now here we have two of the same exceptions. We have lead 2 and we have silver. And then we also have strontium, barium, and calcium. Those are group 2 metals. So if you see calcium sulfate, not soluble. Iron sulfate, soluble. The bottom is a list of rules pertaining to things that are mostly insoluble. So hydroxide compounds and sulfide compounds are generally insoluble except over here. This exception, I think, is a little silly. If you have lithium, sodium, potassium, or ammonium, well, that is actually covered in this first rule up here. So I really don't see the need to do that. When I do this, I start at the top and I work my way down. So if I see lithium, sodium, potassium, or ammonium, it's soluble. I don't look at the rest of the rules. So you can kind of ignore that one. If you've got sulfur with calcium, strontium, or barium, it's going to be soluble. If you have hydroxide with one of those, it's going to be soluble. So these three guys like to be exceptions to rules. So they'll make sulfide and hydroxide soluble. They'll make sulfate insoluble. And then we have carbonate and phosphate. These are generally insoluble except with these guys up here. So you might want to make some flashcards. As you're doing problems that require you to predict the solubility of ionic compounds, try to remember them and then check yourself by looking at the list. Don't automatically look at a list to see if it's soluble or not. Okay, so predict whether each compound is soluble or insoluble. So this is nickel 2 sulfide. So we're going to hopefully got some sort of a picture in your head of that list. It might be kind of fuzzy, it might be missing some pieces. But the top row was group 1 metals, lithium, sodium, potassium, and ammonium. Well, it doesn't have one of those. Next was nitrate and acetate. It's not one of those. Next was sulfate, not one of those. So now we're into the bottom of the chart. We're into the mostly insoluble. Sulfide and hydroxide are the first ones down there. Sulfide compounds are generally insoluble except with those group 2 metals. I'll show you the picture now. So we went through here. None of these pertain to nickel sulfide. But here we've got sulfide. So the exceptions are calcium, strontium, or barium. Well, this example is not any of those. So is this soluble or insoluble? Insoluble. So if I had this in a chemical equation, I would give its state as S for solid. It's insoluble. Okay, how about magnesium phosphate? So we go down the list. Group 1 metals and ammonium, no. Nitrate and acetate, no. Sulfate, no. Hydroxide and sulfide, no. Phosphate, way at the bottom. Phosphate compounds are generally insoluble except calcium, barium, and strontium. Is this an exception? No. Insoluble. The way I do this is I have a mental picture of the chart. So one way to get a mental picture is to draw it a few times. Okay, lithium carbonate, soluble. First row, lithium compounds, always soluble, no exceptions. Done. So if this is in an equation, we're going to write AQ for aqueous. It dissolves in water. If there's water present, it dissolves. So this one's soluble. And then this one, NH4Cl, soluble. NH4, those compounds are always soluble. What if you need to do something that's not on the list? Google and Wikipedia are really useful that way. We also have a chart that I really hesitate to give you because people use it too much. This is what you need to be able to do on an exam. If other things come up, they will be in homework, lab situations where you can look up, is it soluble or not? Any questions?